how can little r and big R be 1 for a big range of angles? That seems a little bit mysterious. Well, it's related to the fact that little r became complex. And recall that we're also describing our plane wave, our electromagnetic wave, as complex. So it has something to do with that. So let's think back for a second. Let's get the magnitude of a complex quantity. Okay? So remember, way back, when we first introduced the complex plane, we had the real axis and the imaginary axis, and we had something called r conveniently. And we said r is just this complex number where you're a height a on the real axis and b on the imaginary axis. So the way you can write this position r is it's a plus j times b. Real part, imaginary part. So if you wanted to know the magnitude, if you want to know the length of this, if it were a vector, how big is r? The real part is a, the imaginary part is b, but how big is it in total? Well, if it's written like this, then you'd say, well, its magnitude, if I just draw a triangle and do Pythagorean theorem, it's a square root of a squared plus b squared, all right? But not all numbers will be this convenient, okay? Not all complex numbers are a plus j times b. It's not always that easy. For example, our r, RTE and RTM are complex numbers, and they're very complicated. They have this big cosine and square roots of negatives and all kinds of things going on. So the other way you can get this is you can say r is the square root of r as it's written times r star, where r star is the complex conjugate of r. And complex conjugate is a fancy mathematical way of saying make the j's negative. All right? And we can prove it with a simple case. Let's apply it to this one. Okay? So the magnitude of r would be the square root of r times r star, the square root of r, a plus b times j times r star, a, and then make the j's negative, minus b times j. And what is that? That's equal to the square root of a squared, and then these cancel, a, b, j, g, b, blah, blah, blah. Those cancel, cross terms cancel, and then it's b squared negative, but then the two j's make it positive. So you get the same thing as Pythagorean theorem. Okay? So this is the general way to get that magnitude. Okay, so in our case, what are we trying to do? We're trying to figure out how we could possibly have a big R value of 1 for all these angles. So let's recall what we're really talking about. We're really talking about the irradiance of the reflected plane wave. That's what we're calculating. It was 1/2 epsilon naught c, and then we have r, little r squared, and then we have E naught squared. But where did that come from? Well, this came from thinking about the Poynting vector. The Poynting vector was the E field crossed with the B field. But how do we deal with that cross product? We said, oh, well, it's the magnitude of the E field times the magnitude of the B field times the sine of the angle between them, which was 90 degrees, and that sine of 90 degrees is gone. So it's the magnitude of E and B. And then we substituted the magnitude of B as the magnitude of E over C, and it brought that C down. So the point is, these are supposed to be magnitudes, and we describe them with complex numbers. So really, this should also be a complex magnitude. And then this is a complex number, this R, reflection coefficient, TE or TM, whichever you want it to be. Since it's a complex number, we actually need to do this. We don't just really square it. Typically, when you see complex number squared, it probably means that. You got to go think about what are you really calculating. So if you were to do that, you say, well, what happens when you multiply this by its complex conjugate? Well, if it's a complex exponential that's oscillating, you get e to the j something times e to the minus j something, makes e to the 0, and it cancels. That's the idea, is the E field is circulating in the complex plane. And if you just want its magnitude, it's constant, right? Because it just goes around and around. Its magnitude doesn't change. So that's why we didn't even talk about this before. It really is just E naught squared. But now we have this thing in here. So the fact that that's R squared, what that's telling you is that R is really R, say TE or TM, either one, times R star. TE or TM, either one. And you say, oh, wait, where'd the square root go? Well, really, it's that we multiply it by itself to get the magnitude, and then that squares it and the square root. So because it's big R and it's squared, the square root and the square root go away. All right, so we're not writing the magnitude of R. Well, we are. We're writing the magnitude of R, and we're taking the square root and we're squaring it. Okay. Now, let's do it for RTE. RTE then is just little r TE times little r TE star, complex conjugate. All right, and that's equal to, what was it, cosine of theta minus the square root of n squared minus sine squared theta over the cosine of theta plus the square root of n squared minus sine squared theta. So now we want to take the complex conjugate of that. It's a little tricky. The imaginary part isn't just real obvious. It's not jumping out at you. So what we want to do is make it obvious. We want to pull a -1 out of here, because the square root of -1 is a j. And if we do that, we're multiplying this by a -1. So -1 times -1 is 1. So one of them came out here. One of them was multiplying this. So this is actually going to switch its order. Sine squared theta minus n squared. And this is going to switch its order. Sine squared theta minus n squared. All right? So now in the region we care about, beyond the critical angle, this will always stay real, right? Because now we're in the angles where sine squared theta is bigger than n squared. So this will stay real, and we've acknowledged that those are the imaginary parts. So completely equivalent. This is still r little te. And now all we got to do is multiply it by its complex conjugate. So this would be cosine theta, and the minus becomes plus j times the square root, and it's going to fit sine squared theta minus n squared over this one's complex conjugate, cosine theta, plus becomes minus j times the square root of sine squared theta minus n squared. And now maybe you can see that this cancels this and this cancels this, and big R is equal to 1. And the same thing would happen for big RTM. You can look at the form of the equation and you can see the exact same thing would happen. Now, it's not the case that every time you multiply something by its complex conjugate, you get 1. Okay, that's not the case. It's just if something happens to be in this form, real minus imaginary over the same real plus the same imaginary, then that thing's, multiply that by its complex conjugate. It will happen to always give you 1 because of the way things cancel. It's not always true of all complex numbers. It's just the way this one is set up. But it's the reason that independent of angle, as long as you're in the case where this stays real, which is beyond the critical angle, it's always 1. Now you may say, surely there's more going on, and there is. Okay, the complex refractive index causes other things to happen with regards to phase, and we'll get to them later. But for now, let's just enjoy the fact that big RTE equals 1, and we have this case where the reflection coefficient is 1, therefore all the light is reflected. And this is called total internal reflection, something you may have heard of, and now we have described in grotesque detail. Total internal reflection. We can show you total internal reflection with our milky fish tank here. So I've got my fish tank, a little bit of milk in it so you can see the beam as we've been looking at. And now I'm going to send my plane wave in. And if I send it at a really high angle, you can see what's happening is it's coming out and it's going away from the normal. So it's coming out here somewhere. There it is, right there. So So it's coming out. Now, as I increase the angle of incidence, suddenly you can see, there it is, in total internal reflection. Right? And if I come up here, nothing, nothing, and then very suddenly it appears. So I go, 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 and there it is. You can see it's kind of a sudden transition, and it's supposed to be, according to that equation. And then, once you have total internal reflection, it stays very strong. It's not changing in intensity as I go across there, but it does suddenly go down as I come this way. Okay? So, okay. So that is the basic phenomenon of total internal reflection.